set is special in some way, that we have a characterization of how you can write it, and that stems from the fact that when you have a homogeneous system, the particular solution is there is a particular solution that is the zero vector. Okay, so in general then, for a linear system in any particular solution, P, the solution set, it looks of this form, P plus H. If you give me a linear system, I can write its solution set in this form, where H satisfies the associated homogeneous system and P is any particular solution. Now this one we are going to prove. I am going to go through the argument. It's not very long, but it involves two steps. This says that the set of solutions can be written in this form. Set of solutions equals this set here, where P is any particular solution. So this is two sets, a set of solutions and this set here. To show that two sets are equal, the most straightforward thing to do, not the only thing to do, but the most straightforward thing to do, is to show that each one is a subset of the other. And that's what we're going to do here. To give the proof, I couldn't fit it all on one slide, so it's on the second slide too. But to give the proof, I'm going to show, first of all, that if a vector is in the solution set, then it is in this set also. And then on the second slide, I'm going to show that if a vector is in the set given, the P plus H set, then that vector solves the system. So that's called mutual inclusion. I'm going to show set inclusion both directions. If a vector solves the system, then it's of this form. Okay, so to show that, what do I have to do? Well, you assume that S solves the system. So then I want to show that S minus P is the right form for H. If I show that S minus P equals H, why then S equals P plus H. Okay, so what is H? H means that when you plug the components of the vector in, then you got to get 0. That's what homogeneous system means. Okay, so I'm taking the components of S minus P and plugging them into each equation. I'm only going to show one equation, of course, but I'm taking the components of S minus P and plugging them into that one equation. Well, you do some algebra here. So let's see. You distribute the A's, and you get A's times S's minus A's times P's. Well, A's times S's gives you D. That's exactly what S is, a solution of the system. So that's exactly what that means. A's times S's. A's times the components of S gives you D. And P is a particular solution also of the system. So so A's times P's gives you D, and they're D minus D 0. So that's exactly what I needed to show. I needed to show that S minus P has the right form for H. H is a vector that has the property that when you plug it into the left-hand side of the linear system, it will give you 0. Okay, so that's half of the argument. I have to show the other half of the argument. The other half is that if a vector has this form, particular solution plus a member of the set of homogeneous solutions, then it is a solution of the system that you started with. So you take a vector of the form P plus H, and you want to show that that P plus H solves the given system. So that's just a matter of plugging the components of the vector P plus H into each equation. So here I plug the components of the vector P plus H, the first component all the way down to the nth component of the vector P plus H. I plugged it into the equation. I did the obvious algebra. I distributed the A's. So I have the
congestion.
A's times the P's, and the A's times the H's. A's times the P's, P is a particular solution of the linear system. So A times the P's gives you D. H, on the other hand, is a solution of a homogeneous system. And I know we only just saw the definition a few minutes ago, but the homogeneous system is the one with zeros on the right-hand side. So A's times the H's gives you 0. And D plus 0 gives you D. Whoops. So in general here, we can always write the solution set in this form. We can always write the solution set in the form we started out the day by looking at here. You have particular solution, and here you have what the homogeneous solutions are. Vector times a letter, vector times a letter. Okay. Now, we like this for a number of reasons. One is that I can write down the solution of a linear system and understand completely what the solution set of a linear system looks like. It looks like any particular
Skyscraper design. Skyscraper design.
A solution, any particular solution at all that you find can go there. And then here is vector times a letter, vector times a letter, vector times a letter, etc. I just copied that from the solution of the homogeneous. That's the H part. And in particular, what happens here is that by looking at the previous slide, but there's the previous slide, by looking at the previous slide and understanding what the various parts can be, I can see that solution sets of linear systems have three possibilities. Solution sets of linear systems are either empty, have one element, three possible parts can slide, but there's the previous slide. By looking at the previous slide and understanding what the various parts can be, I can see that solution sets of linear systems have three possibilities. Solution sets of linear systems are either empty, have one element, that is to say there's a unique solution, or else have infinitely many elements. Those are the three possibilities that can happen. Here I've got a nice box on the next slide that I'm going to point to. So in this box, this little array here, there are two possibilities. Either a particular solution exists yet, or else it doesn't. And we've certainly seen linear systems that don't have a solution, so that would be the bottom line. Well, if a linear system doesn't have a solution, then there's just no solution. That's all there is to it. On the other hand, if a linear system does have a solution, if a linear system does, whoops, on the other hand, if a linear system, then there's don't have a solution, so that would be the bottom line. Well, if a linear system doesn't have a solution, then there's just no solution, that's all there is to it. On the other hand, if a linear system does have a solution, if a linear system does, whoops, I went too far. If a linear system does have a solution, if there is a P that you could write there, then what can happen for the homogeneous case? What can happen with homogeneous systems? And you'll remember from a couple slides ago, homogeneous systems are just like regular systems, except there's one thing that can't happen. So here we go in the box. Homogeneous systems can have infinitely many. Homogeneous systems can have unique, but they can't have the other case. They can't have no solutions. So we get this array here. So the number of solutions to the homogeneous system can be one or can be infinite many. And if the number of solutions to the homogeneous system is one and a particular solution exists, why then the system you started with has a unique solution. If the number of solutions to the homogeneous system is infinitely many and a particular solution exists, then the system you started with has infinitely many solutions. And of course,
The solution to the system, the possibility of how many ways you can reach out your goal, depend on two factors. Does a road particular solution exist? Yes, then you at least have a way to get there. No, then you stuck no solution. Are there multiple paths, homogeneous solution, just one direct road, unique solution, many different roads, infinitely many solutions. Breaking down the table, particular solution. If we had particular solution, number of homogeneous solution. If it's yes, one solution, only the trivial solution. Yes, we might have these two result, infinitely many solution. We might have one solution or infinitely many solution. Total solution type, yes. Unique solution, one way to solve it. Infinity solution, many ways to solve it. Now, particular solution, there is no particular solution. Number of homogeneous solution, only one solution. No, infinitely many solution. Total solution type, it will be no solution, no solution. Real life example. So, unique equation, one road to success. Example, solving for one unknown in the equation, equation 2x equals 6, solution x equals 3. There is only one answer, a unique solution for this equation, which is 2x, yeah. Infinitely many solution, many roads to success. Example, a system where two equations represent the same line. Two equations represent the same line. Equation y equal 2x plus 3 and equation 2y equal 4x plus 6, which is simplified to the same equation. Okay, yeah, which is divided. There are these are the same line, so every point on this line is a solution. Infinitely many solution. Okay. There's no solution, block roads. Example, parallel lines that never intersect. Equation y equal 2x plus 3 and equation 2y 2x minus 4. Since these lines never touch, there is no solution between them. Yeah. Key takeaways. If you have at least one particular solution, you always got solution. So if we had one particular solution, we always got solution. If the homogeneous system only has the trivial solution, zero vector, a trivial solution, zero vector, we got a unique solution, which is one solution. If a homogeneous has infinitely many solutions, we got infinitely many solutions. So particular solution, always we got solution. A homogeneous system only with the trivial solution, zero vector, we got a unique solution. Homogeneous system, infinitely many solution, we got infinitely many solution. Is no particular solution exists, then whole system has no solution. And minigame, what kind of solution set? Imagine you solve a system and find that there is one particular solution. The homogeneous system has two free variables. Which case is this? So there is one particular solution. So one particular solution, we said unique solution. The homogeneous system has two free variables, so we had infinitely many solutions. So the solution would be this one. Reply with your answer. Exist. So the system is consist. The homogeneous solution has two free variables, which is mean has infinitely many solutions. This means the total solution set is one. Particular solution plus infinitely combination. Final takeaway. If a particular solution exists, the system is solvable. If a particular solution exists, if the homogeneous part has a free variables, the system has infinitely many solutions. More free variables, more direction to explore the solution space. Bonus challenge. What if no particular solution exists, but the homogeneous system has two free variables? So since no particular solution, there is no solution. That's easy. The system is inconsistent, meaning no valid starting point. The homogeneous system has two free variables, but that only tells us how solution behave in particular solution. If there are no particular solution, then even adding homogeneous solution won't magically create valid solution, so the system has no solution. Final knowledge post homogeneous solution, one help if particular solution exists, no particular solution, no solution at all. A system with no solution is called an inconsistent system. Boss level challenging, okay. Suppose you row reduce a system and find this row in augmented matrix. What does this tell you about the system's solution? Okay, so x plus y plus z. Here we had two free. Okay, free. This is one free. I think there is no solution. Why is the answer C, no solution? Let's break it down step by step. Understanding the matrix, we have the augmented matrix. The second row is all zero. Zero equals zero, which is fine. It means there are dependent equation. The third row is a big problem. Plus x plus y plus equal 4. 0 equal 4, which is simplified to the contradiction. This is false statement. It means something impossible happened. In math equation like 0 equals false, which is means system inconsistent, and consistent system has no solution. We don't even got particular solution to start with. Now applying the solution table. Does a particular solution exist? No, so there is no solution. In, there are contradictions. Does the homogeneous system matters? No, because we already had no particular solution. Final takeaway. whenever you got a row like 000, non-zero number, boom, inconsistent system, no solution. You did it. You are now solution set pro, bonus challenge. You cracked. Bonus fun challenge. Now that you are a pro, try to making make system equation infinitely solution. Okay.
Of course, the no solutions case means that there's no particular solution. Okay, and just to close, let me sneak a word in here before I let you go. So an important special case is when the linear system has the same number of equations as unknowns. So when you look at the matrix of coefficients for that linear system, there's two cases. Either it has a unique solution or else it is or else it doesn't. So in the case where the matrix of coefficients of the homogeneous system has a unique solution, you say that that matrix is non-singular. Non-singular here means something like normal or usual or doesn't stand out or not particularly problematic. On the other hand, if the homogeneous system has infinitely many solutions, if we're looking at that case, if the homogeneous system with that matrix of coefficients has infinitely many solutions, then we say that the matrix is singular. And singular here has the connotation of being a little bit odd or a little bit troublesome or mathematically interesting, whatever way you like to say it. Now, there is something a little odd, a little peculiar about the terminology. It is the case, I didn't mess this up. Non-singular is associated with unique solution. I know that's confusing, but it's the right word. It's the standard word. Non-singular singular is associated with the unique solution, and singular is associated with non-unique solution. That's true. But this is the standard way of using the words, and again, you have to think of the other meaning of non-singular and singular. If you're like reading a Sherlock Holmes novel and it says, the singular case of the dancing men, singular means stands out or peculiar or interesting or somewhat unusual, and that's what's intended to happen here. Non-singular case is the case where you find that the linear system has exactly one solution, the homogeneous system has exactly one solution. That's kind of the expected or the usual or the typical. Okay, very good, very good. That ends the first chapter, so I'll let you go, and it ends the first section, so I'll let you go, and I'll see you next time with the second section, vectors in space. Very good. Okay, bye-bye. Hello. Hi, hello. Ready for the second section of the first chapter. So because this is the second section, we are going to ready for the second section of the first chapter.